What if I told you that every electron in the universe has its own home address? Not a metaphor, an actual address. With a building number, a floor number, a room, and even which way it's facing inside that room. That address has four parts. Chemists call them quantum numbers. By the end of this video, you'll understand them so well you could explain them to a 5-year-old and also solve them on your CSIR-NET or GATE exam. Let's go. Imagine an atom is a giant apartment building. Electrons are people who live in this building, and every single one needs a unique address. No two electrons in an atom can share the exact same address. That one rule is going to explain almost everything you learn today. An address needs four pieces of information: which floor you live on, which shaped room you live in on that floor, which direction that room faces, which way you're spinning while you are in it. Yes, we'll get there. That's it. That's the whole idea. Now let's turn each floor of its of this analogy into real chemistry. The first number is n, the principal quantum number. Think of it as the floor number 1, 2, 3, 4, and so on, never zero. Never negative, never a fraction. The higher the floor, the further you are from the ground. And in our building, the ground is the nucleus. Higher floor means more energy and more space. An electron on floor 3 is farther from the nucleus and holds more energy than one on floor 1, just like the penthouse is farther from the lobby. Master's level layer. N determines both size of the orbital and to first approximation its energy. For hydrogen-like species, energy depends only on N, following E is equal to minus 13.6 Z square slash N square electron volt. The number of subshells available on a given floor also equals N. Floor 3 has three types of rooms. Floor 4 has four. This is exactly why the above diagram fans out the way it does. Now every floor has different types of room. Some rounds, some dumbbell shaped, some shaped like a floor four-leaf clover. That's L, the azimuthal or angular momentum. Quantum number, it tells you the shape of the electron's room, which we call an orbital. L can be any whole number from 0 up to n minus 1. We get these shapes and nicknames. 1 is equal to 0 is called S, a sphere. 1 is P, dumbbell. 2 is D, the clover. If L is 3, it's F, something even more elaborate. Master's level layer. L quantizes the orbital angular momentum of the electron, given by under root L into L plus 1 H. It also governs the number of angular nodes. An orbital has exactly one of them. This is the number that splits energy levels in multi-electron atoms because L affects how well an electron is shielded from the nucleus. S electrons penetrate closer to the nucleus than P, which penetrates closer than D. That's the real reason 4s fills before 3D. Here where it gets fun. A dumbbell-shaped room can be oriented in different directions in space, pointing along x, y, or z. The orientation is m, l, the magnetic quantum number. ml can be any integer from minus 1 to plus 1 including 0. So if 1 is equal to if L is equal to 1, a p orbital ml can be minus 1, 0 or plus 1. Three possible orientation, which is Exactly why you have always seen three p orbitals: px, py, pz. Master's level layer ML specifies the projection of orbital angular momentum along a chosen axis, conventionally LZ MLH is equal to MLH. This number is what actually splits spectral lines in a magnetic field. The Zeeman effect. Without an external field, all these orientation are degenerate, meaning equal in energy, which is why p orbital normally looks identical in energy until you apply a magnetic field. Last piece, even after you have picked the floor, the room shape, and the direction it faces, a room can still fit exactly two peoples as long as they are spinning opposite ways. Imagine each electron is either spinning clockwise or counterclockwise. That's ms, the spin quantum number, and it only has two possible values, plus half or minus half. This is the final piece of the dress, and it also where the Pauli's exclusion principle comes from. Two electrons can share the same floor, room orientation, but never the same spin. That's why every orbital holds a maximum of two electrons. So the complete address of any electron looks like this. N tells you the floor, L tells you the room shape, ML tells you which way that room faces, and MS tells you which way the electron is spinning inside it. Four numbers, and no two electrons in the same atom will ever have all four match. For your exams, where you are asked to find the number of orbitals or electrons for a given n, remember total orbitals on a floor n square and total electrons on that floor 2n square. That's a single shortcut solves half the quantum number. Question you'll see in CSIR-NET and GATE. That's quantum number from a 5-year-old apartment building to full exam ready formalism without changing the underlying picture once. If this clicked, follow Camwall for more concept broken down the same way. See you in next one. Thank you.